Alrighty, I think it's about time to get going. So while we let the last stragglers filter in, I just want to say good morning, good afternoon, good evening. Welcome to Paleo Perks. My name is Elizabeth Seibert. I'm one of the organizers of Paleo Perks, and today it is my great pleasure to have Gabi Serrato Marx giving a talk. And so for those of you who haven't been in a Paleo Perks seminar before, we just want to give you a little bit of housekeeping and an introduction to what's going on here. So we want to mention that Paleo Perks values the participation of all folks interested in paleo sciences, and we'd like to remind you to please abide by our code of conduct during today's seminar. We'd also like to remind you to please mute yourself for the duration of the talk, and that for questions, if you have any questions, we'd like to ask you to please send them by chat to Raymat, who is the Questions at Paleo Perks host. Any other technical issues that you run into during today's talk should also go directly to the Questions Paleo Perks host. We'd also like to remind you that we are accepting nominations for our potential speaker pool. So if you have an excellent early career scientist you'd love to hear a talk from, please nominate them. We also accept self-nomination. So if you would love to give a talk, please nominate yourself. We've also had some email list growing pains recently, so please check your spam, though if you're in this meeting, you've probably gotten this Zoom link at this point. And then finally, we do have a Survey Monkey that just asks for who is in today's seminar. Who are you today? What is, and if you wouldn't mind filling that out, it's completely optional, but it helps us understand who's actually coming to these seminars and keep engaged. So we've dropped a link to that in the chat window. And for those of you who haven't been to one of these before, this is how today's going to go. We've got some welcome and announcements. That's this, like about next 2 minutes. Gabi will give her 30-minute talk. We'll have a moderated Q&A, and then we'll send you to breakout rooms for science and social discussions. After the hour is up, we have a 30-minute tea time where you can hang out and have a chat with Gabi and see how science is being done or any other particular questions you'd like to get answered. And then this is just a final reminder to send any questions or issues you have via chat to the Questions Paleo Perks host, and that is Raymat today. So without further ado, I would love to introduce today's speaker, Gabi Serrato Marx. Gabi got her bachelor's in Earth and Oceanic Science, got her PhD from the MIT-WHOI Joint Program in Marine Geology and Geophysics. She's currently a postdoc at MIT and is also a freelance science writer. And so without further ado, I'd like to hand the screen share over to Gabi, and we'll hear her talk on paleoclimate.
Thank you so much. I'm gonna share my window. Okay. Hopefully you can see this now, my title slide. Perfect. I see a nod from Elizabeth. So thank you all so much for being here. As Elizabeth said, I recently defended, so this is gonna be slightly overlapping with my defense talk, but I'm going to be talking today about Speleothem that I've been working on from northern Mexico that grew during the first millennium of the Common Era. And of course, this research could not be done without a lot of other people. So I want to start with them instead of putting them at the end. So we have here Laura, who is at UNAM in Mexico, David, my advisor at MIT, Kathleen, who is at UC Irvine, and her student Kevin. And then there's also a lot of other people who have been part of this project who are not yet, who are not in these pictures, in part because they're always covered in mud or because we only have Zoom meetings. But this is a big project that I feel really lucky to be part of and that I really have enjoyed being part of. So a big shout out to all of those collaborators that we've worked with. But to give you a sort of an overview of what I'm going to be talking about, most of Mexico is very dry. It's arid or semi-arid. And that means that a lot of the areas that we're working in, this is from San Luis Potosí in northern Mexico, a lot of those areas are so dry that you actually get these evaporite deposits mud cracks, you have lots of cacti. I've heard it looks like Joshua Tree National Park, though I've never been there, but it's very, very dry. But a lot of the Speleothem records that we have, for a variety of reasons, are actually coming from the Yucatan Peninsula in Mexico and then down into Belize, which is here. So to orient you, this is Florida, all the way up and around Louisiana, Texas, and Mexico here. And so a lot of these, each of these orange dots is a published Speleothem record. And of course, some of them are doubled up where there's multiple Speleothems from each cave that's highlighted here. But a lot of the areas where these records are coming from look like this. It's a lush rainforest. It's not arid, definitely not arid, maybe not semi-arid ever. And they do have seasonal rainfall, but this is a place where it's just a different climate and different vegetation from a lot of this arid area here. You can sort of see the dry brown stuff all the way up here in northern Mexico. And so part of what we wanted to work on is filling in this gap. What does paleoclimate look like in this area? This is a more scientific version where here this is all karst, and each of these white dots again is a stalagmite record. And all of this karst here doesn't have any published Speleothem records from this area. And there's a lot of reasons for that. Part of it is sort of geopolitical, that this northern part of Mexico was not accessible to scientists for a long time. And it's now a great place to work. There's a lot of places in Mexico that I think are great places to work, but this part here with karst doesn't have any published records. So our project was focused on filling in this part here. And the main reasons behind this, in addition to missing that long-term data, is that this area is already water stressed, and it will continue to be water stressed in the future, where there is a lack of recharge to the aquifer. So there's more water being drawn out for drinking water, for agriculture, everything than is being added back to it. And the population in this northern Mexican area is just growing. So that is getting worse, not better. And so that's another kind of significant motivator for why we wanted to do this project. So going forward, I'm going to show you some actual results and what we did. So this part up here is Teotihuacan. This is a huge city in northern Mexico that was thriving in the first millennium of the Common Era. And so this is one of the biggest pyramids here. And this area is called the Street of the Dead here. And this is an area that has been understudied compared to the Maya civilization in the south, in the Yucatan Peninsula, but it was huge. I wouldn't say it was quite as large in terms of geographic extent, but this was a really bustling city with hundreds of, or definitely tens of thousands of inhabitants. Depends on which estimate you want to look at, whether it was reached 100,000, but lots of inhabitants here. And the timeline of what that looked like was that in the beginning of that first millennium of the Common Era, this is the early classic period of Teotihuacan. Then around 550 CE, there was a depopulation event. And between 500 and 650 CE, we went from about 100,000 inhabitants to only about 20,000. So it was a really, really rapid decline. And then after that, into the Epiclassic, the society was very different from how it was before. In this area here, there was a lot of environmental engineering, there was vast agriculture and irrigation. And then afterward in the Epiclassic, there just wasn't that level of engineering and of kind of environmental control. So that's an indication that this was not as much of a thriving society. And so we're trying to figure out, in collaboration with archaeologists and lots of other paleoclimatologists and ecologists and everybody, what environmental pressures were significant in this area, either during the depopulation or before and after, because that's just something that we don't have a lot of data on in terms of high resolution records with low dating errors. So that is what we tried to work on. But it's important for me to note that there were these technological controls. This society had really advanced irrigation, canals, dams. This is a modern example of the types of canals that they had. They had floodwater control. This is not a case of it got a little dry and then the society collapsed. This is a society that had adapted to their environment and that were very adept at working within the environmental controls that they were experiencing. But at a certain point around 550, a combination of different factors led to that collapse. And so it's really important for me to note that this is not a simple story of everyone left because there was one drought. It's not exactly a causation like that. So we're looking for co-occurrence, maybe looking for correlation, but there's a lot of steps needed to turn that into a causation. This is the cave where I worked. So it's this really, really beautiful cave where we have to walk down about 100-ish feet of ladders down to get to this chamber. It takes us about an hour and a half to get down into this chamber. You can see it has beautiful white active growth. There are these pools. There's actively dripping water, so it's a wet cave, and it's just a really beautiful place to visit. So I feel really lucky that I've gotten to visit this place. But we got a stalagmite from this cave that is called CP2, not a very creative name, but it's Cueva de la Puente number 2. So that is shown here in cross section, where in case you're not spending every day looking at speleothems, this part down here is the base of the stalagmite where it was attached to the cave floor. And then this part here is the top. So that would be the youngest portion of the stalagmite. But what you can notice here is that it's actually kind of chopped off in a way. And that's how we found the stalagmite. It was not, this isn't like a cut that we made. So we looked and looked for sort of the top of this stalagmite that would form a nice rounded shape that we expect from a speleothem, in case it had broken off or any other number of things that could have happened to that top portion, but we have not yet found it. I think we'll probably keep looking every time we go to this cave, just in case it's there. But for now, we're calling this the top of the stalagmite, and this is the bottom. And so we used uranium thorium dating to find out that the bottom portion here started growing about 290 CE, and the top portion here is about 978. And the age depth model we created with that uranium thorium dating looks like this. So the stalagmite grew in this diagram basically from the bottom left to top right, where it started around 300 and it grew up to about 900. And again, this whole time I'm going to be talking in CE, and I know that is different from years before present or millions of years before present or whatever time scale everyone else normally works on. So just note that this is CE. So in this time scale, we would right now be in 2020. So just a note on that. You can see here that each of these black bars here is the 2 standard deviation error or age uncertainty. And the envelope around the blue line here is the uncertainty on that age depth model that we used. We used COPRA for that to create 2000 Monte Carlo simulations through those dates. And you can see here that the stalagmite on the right has alternating white and gray fabric. And these white portions here grew much more rapidly than the gray portions. So here's one gray portion and here's another one here. And that's significant because the age model does have these rapid changes in shape. And so it's important to note we are aware that there are these major changes in growth rate. And we've taken a lot of dates throughout all of these to try to get a sense for what's going on there. And we are still potentially going to get another date or two to really refine this part and this part. So we're still working on this age model and the stalagmite overall, but this is the almost finalized age model. And we're really excited that we saw significant correlation between the proxies. So we took delta 13C, delta 18O, and magnesium calcium. And all three of those proxies show correlation. This is a Spearman's rank correlation, so it's not assuming linear relationship between the proxies, but these rho values were high enough that we felt like they were being controlled by the same processes, but also not so high that we were super concerned about the kinetic effects or other types of weird things that can go on in caves. So here we are using delta 18O, delta 13C, and magnesium calcium ratios as proxies for paleohydrology. So each of these have different controls, and that's something that we can definitely talk about in the breakout rooms or during tea time about all the complex controls on speleothem geochemistry. But just for the sake of today, I'm going to be talking about these in terms of paleohydrology, where when these change, that's to us indicating a change in how wet or dry the environment was above the cave. So let's look at data. I'm gonna stack up the proxies here in our favorite spaghetti plot where we have delta 18O, and then we'll have the other two proxies here. And I've plotted them where wetter is on the bottom and drier is on the top. And that's in part because we're really interested in looking at droughts and dry conditions. And so I was really trying to find these sort of peaks that occurred here. And so that's part of why I've plotted them that way. And also because this is the way the numbers actually go. So the y-axes are not reversed. So this is all three of those proxies together. And these missing gaps here and here, we are going to fill in. That's partly a product of COVID and also just because of the change in growth rate. This overlaps with that small gray portion that we actually initially avoided sampling because we weren't quite sure what was going on there, but we've since filled it in, and except for this part. So we're still going to get that data. But what we're really looking at here and really interested in is the places where all three of these proxies are indicating a drier or dry conditions at the same time, because that means that we have robust indicators that there was actually something dry going on here, for example. So I look here between 300 and 400, and all three of those proxies are seeing that same spike up. And then later on, there's a similar spike upward, but we're missing this data here. So I'm really excited to see what these two proxies show. But here we do see a long-term drought that occurred here also, and again, throughout this. But what we can turn this into is a z-score. And because magnesium calcium has the greatest coverage and the highest resolution, you can really see the difference in the resolution between this line here and this line here, where there are a lot more dots just on the bottom line. We use magnesium calcium primarily for the rest of the analyses. So this is now turned into a z-score, where this is saying if it reaches 2 here, that means that the value was more than 2 standard deviations away from the mean. Same thing for here. And so I've color coded this where the orange vertical bars here mean that it's outside of that 2 standard deviation envelope. And a yellow bar means that it was only 1 standard deviation outside of it. And blue means that it was 1 standard deviation wetter. And we don't have a dark blue because there actually were not any periods that were more than 2 standard deviations in the negative direction here. So these droughts are really the significant changes that we're seeing. And so during this first portion of the first millennium of the Common Era, from 300-ish to 500-ish, that is when we had, according to archaeologists and the current understanding of the region, that's when there was a lot of expansion at Teotihuacan. And that's when there was that agriculture, irrigation, really incredible hydrological engineering that you sort of just have to picture in your mind, because there aren't images of it. There aren't even really reconstructions. So I can't even show you like an artist's reconstruction of what that looked like, but there's paragraphs and paragraphs that describe it. And so I encourage you to eventually go visit it or read a lot about it, because it's a really incredible thing to imagine. And the Later on, around 550, that's when we had a depopulation event between 550 to 650. And that's when there was no longer any agriculture or water management, and the population was much lower, like I talked about before. And so what we noticed immediately was that this large orange bar here overlaps with that depopulation. And so again, I'm not doing any, drawing any direct lines between this drought causing the depopulation, because I think it's much more complex than that. But here, what I think is really interesting is that between 300 and 400, when the civilization was really thriving and there was broad brush, like things were good in the region, there were these extreme droughts. And so this to me indicates that the civilization was resilient to these droughts or this very wet period, even though there were these later droughts that maybe did coincide with depopulation. And so I think it's a story of both climate resilience and potentially like climate impacts in this area. But comparing it to other speleothems and records from the area, the story gets even more interesting. So this is a high resolution record from the Yucatan, from Martin, Medina, and Lizalde. And what he found here is these terminal classic droughts that are very popular and very interesting in the Yucatan, because they are these series of droughts that occurred at the same time as the collapse or depopulation of several Maya sites. And again, just want to super reiterate here that there are still Maya people. There are 6 million Maya people still in Central America. And archaeologists don't know precisely what ethnic group was at Teotihuacan, but I think we can assume that there are still hundreds of thousands or millions of the same indigenous group and other ones in this area. So this is not a collapse in the sense of like everyone was gone. There's dispersal, there's a lot of complicated population dynamics here that is not my specialty, but I just really want to point that out here. So finally, in this region here, we have these terminal classic droughts that are occurring at the same time as either really nothing significant in our record from CP2, or at the same time as wet periods, but these aren't totally synchronous. And again, here we have this long drought, and that occurs at the same time as wet periods in the Yucatan. So it was clear pretty much from the get-go that these were not going to show the same signal. And that's okay, because in the modern Mexican paleoclimate or modern Mexican climate, these two areas are not having the same hydroclimate. So that's reasonable. But we were really interested in looking at the dipole that has been hypothesized between northern-ish Mexico and southern-ish Mexico. And I say ish here because it's sort of a left-right diagonal line here that splits the two, rather than like a latitude here, because the Yucatan Peninsula comes up north. So it's this split here between northern Mexico and southern Mexico, where there are different responses to the same forcing. So for example, this is the Atlantic multi-decadal oscillation, or variability, and the NAO here, and El Nino. So all of these are from Tripti's paper, Tripti Bhattacharya's 2017 paper, where she talked about this potential dipole. But for the first millennium of the Common Era, it was really difficult to prove that this dipole was present, or to try to even see that, because there aren't a lot of high resolution records from northern Mexico. That's that same karst record I was showing earlier, where there's just missing Speleothem records all throughout the north. And so this is an area where it would be really valuable to have more high resolution records. And so that's what we tried to do. So more quantitatively, we used empirical orthogonal function analysis to compare the Cariaco Basin and then speleothems from here, here, and here. So these are all speleothems in sort of the middle part of Central America. And then Juanacatlan, this is a sediment record. And then CP, this is another Speleothem. So a mix of different types of records here, but we stacked them all up and used this EOF analysis, which looks at, rather than saying, oh, well, this orange is at the same time as a blue, or whatever kind of hand-wavy barcode type thing I'm showing you here, it's a really quantitative way to do that. So when we ran this analysis, what we found is that during the first part of the first millennium, between 300 and 500, the conditions in northern Mexico and in much of Mexico were actually wetter than they were for the rest of the millennium. And so here, wetter is down below, drier is up top here. And this is the first mode of variability, which indicated that there was this slow but significant increase from very wet conditions to dry conditions here. And so by the time we got to 550, approximately the same time as the depopulation, that's when there was really, had already been a switch to drier conditions. And the EOF analysis shows different responses at different sites. So let's look at that. Oh, I already talked about that, sorry. And so here, each of these dots indicates one of those sites that I was talking about. The darkness of the green or purple color shows where we are in terms of correlation with that first mode of variability that I was just showing, where it was slowly increasing upward, kind of a Nike swoosh, if you will. And the purple means that it is anti-correlated, so it was not doing the same thing, and green means that it is correlated. The inner circle here means that's the response for the low end of the 95% confidence interval on the age model. The outer circle is the upper end of the 95% confidence interval, and then the middle circle here, so not the bullseye, but the middle part around here is the mean or median age model. So that middle one is actually the one that's most important because that tells us what that mean is. But this is a really nice analysis that does take into account the error on the age model. So that's why we use this. This is code written mostly by Tripti Bhattacharya. So what we see is that at CP, at my site, and then at Huxtlahuaca and Juanacatlan, which are these not quite northern Mexican sites, but almost left or western sites, have the opposite response of, the Yucatan sites and the Cariaco Basin. And the size of the dots, I forgot to say that, the size of the dots are indicating the weight at that site. So there's a very heavily weighted, basically positive correlation here on CP and negative correlation at Cariaco and Satna here. So at a first level, this is supporting the dipole during the first millennium. It is sort of matching up with that previous plot that I was showing before, where Tripti had the modeling results showing that there was a differing response that basically split right around here. So the next steps on this are adding more speleothems and more sites to this so that we can even have a more robust estimate of what was going on at this period. And my collaborator, Kevin at UC Irvine, has another speleothem that'll go right about here. And so we're going to just keep refining this. But for now, I think that this is really strong evidence that there was that similar dipole of differing responses between the two. What's interesting is that this is almost identical to the modern correlation with rainfall at Teotihuacan. So this darkest green square here is the one-to-one correlation where it's correlated with itself. And then out here is Cueva de la Puente, the site I'm reporting on, and Huxtlahuaca here, which is a southern Mexican site. And this site is a really, really rich archive of speleothems, and they are super valuable in a lot of ways, and they're also correlated with Teotihuacan rainfall. But when we looked back at sort of comparing CP versus Huxtlahuaca with Teotihuacan, we're seeing so far that Cueva de la Puente may be slightly more correlated with the Teotihuacan rainfall. So if people want to do direct kind of line drawing between paleoclimate and civilization at Teotihuacan, we're trying to see if these northern sites might make more sense or might be an important addition. So comparing that, it looks like there are definitely places where they strongly disagree, even though they are in the same part of that dipole, the same half of the dipole. So for example, between 500 and 600, there's this drought in CP and a wet period at Huxtlahuaca. And later on, same thing, a wet period in CP with long-term drought in Huxtlahuaca. And so we're still refining whether this has to do something with age model uncertainty, but based on the first analysis here, it looks like there's still some differences that we need to sort out and to sort of understand why these are happening. So this is still ongoing also. But so far, we have not seen any decadal scale droughts in the modern record. So sorry, just to point out again here, these are decadal scale droughts both in the Huxtlahuaca record and in the CP record. So this is something that we're seeing pretty frequently throughout this paleo record. But if you looked just at the past 100-ish years of modern Mexican paleoclimate, it looks like there aren't those decadal scale droughts. And so you could sort of cross your fingers and say, well, hopefully we won't have significant droughts that last for years and years. But that might not be the case based on the paleo record. And so doing that same analysis here, these are only droughts or dry periods or wet periods that lasted for a year, maybe 2 years maximum. So this is something that could have implications for future water management and trying to ensure that this region can prepare for long-term droughts and not just the shorter wet or dry periods that we've seen so far. So to finish up, the take-home points that I want to really highlight here are that there were significant droughts that were occurring at the same time as depopulation, but they also did occur at the same time as a thriving civilization. That northern Mexico is a great place to do research, and it's a really rich archive for more data on Teotihuacan and the rest of Mexico. Remember, 74% of which is arid, and that precipitation dipole does seem like it was present during the first millennium. So, of course, next steps is always more caves and more data, but we are working on another Speleothem. This is one that grew for even longer than that CP2 one, so it grew for about 6,000 years. So this will be someone else's project because, as Elizabeth mentioned, I just defended, so this will move on to someone else in the project, but this is Kevin here working on his Speleothem, so we have more data coming and we're really excited to combine it all in a rigorous way. So thank you so much for listening, and I've left my take-home points here, but we also have a website where you can learn more about what we're doing and see some really cool pictures of the cave monitoring efforts. So you can learn more at this bit.ly link /SEMA-project, and it's case sensitive. So thank you so much.
Wow, thank you, Gabi, for that really excellent talk. We do have a few questions that are starting to come in. So again, please remember that if you do have questions you'd like us to ask Gabi, you should send them to the questions at PaleoPerks, and we will get to them. So the first question we have is from Philip Bone, who asks, do you have plans of collecting data from more northern states like Tamaulipas or Nuevo Leon? And I'm so sorry I butchered all of those.
That's okay.
So you can maybe help with that.
Yeah,
and I'm just going to pop the question text in chat as well.
Perfect. So the site that Kevin is working on is in Tamaulipas, which is a state that is just to the north and east of San Luis Potosí, where we're working. And so there are plans to work there. Nuevo Leon, we have not yet identified any caves there that we're working in. that's in part because our collaborators are based primarily in Mexico City, which is further to the south, but I really encourage people to set up collaborations and try to find ways to get more data from the northern areas, because I think it's going to be really important going forward, as I probably overemphasized at this point. But yes, our specific project is working in Tamaulipas as well, in the kind of mountainous area there.
Great. So the next question we have says specifically, looking at your figure 11, or figure on slide 11, your Speleothem figure, could you please elaborate why there are color changes and whether they are related to the growth rates of the Speleothem?
Yeah, I'm gonna just go backwards to it. Sorry if this makes anyone dizzy. Okay, so here is the Speleothem. And the question here is, why are there color changes and what does that have to do with the growth rate? Here, these white ones are much less dense. They're even easier to drill. So this area here is growing much faster. And that's basically just, I kind of think of it as like a brownie versus like a fluffy cake. And so this is a fluffy cake part of it. And then this is the more brownie-like, very dense portion of growth. And so here it grew much more slowly, but it's very, very dense. And so the dates that we have here are more spread out in time, even though they're closer together in depth. And so in these two parts, it's growing much more slowly. It's less material per year. And so that's part of the reason why it's much more dense here. And for example, I break drill bits on this, but I don't break drill bits on this upper white part.
And I think just a quick follow-up to that is, do you think there are any hiatuses, or is it continuous in terms of vegetation?
We've looked really, really carefully, and we've specifically dated, for example, just above and just below the borders between these two parts in color. And we have not yet found any indicators that there is a hiatus, but this part here between 600 and 700 is a part that we want to really make sure that we have that for sure. But we have duplicates or replicates on a bunch of these dates, and we're pretty confident so far that it is continuous growth.
Great. So the next question we have is from Tiffany Napier, who asks, are there tree ring records from northern Mexico? And if so, how do those records compare to Speleothems?
Yeah, great. Part of the reason that we're working with Laura, who is at UNAM, is because she studies tree rings. So tree rings are a great record from this area. The oldest ones extend back to about, I think it's about here, it's like 980 maybe. But it's just the very, very end of the first millennium. And so part of the motivation for this project is to extend that record backwards, because there are really excellent high resolution tree rings, but they don't go back quite as far as we need them to go, to overlap with either the changes happening at Teotihuacan or this earlier portion here. So there's definitely a plan to correlate or work with those tree ring records, and that is upcoming.
Excellent. So our next question asks, I was wondering if you think there is a chance that the proxies are overestimating the drought signature, and that's why you see multi-decadal droughts in the past, but not in the modern.
Yeah, that's a great question. I think there's a lot of different ways that we can calibrate the proxy system. So in this region, we have modern rainfall monitoring happening at the same time as we're doing this cave-based fieldwork. So there are people who live near-ish to the caves who are collecting rainfall, and then we can correlate that with the amount of rain. And so we have that estimate of the amount effect. And that's where having tree rings will come in, where we can compare the stalagmites that grew for longer and sort of overlapped more with those tree rings. We can compare to make sure that we're not overestimating, and we can use those monthly estimates of the amount effect, which we do have to make sure that we're not overestimating that. But that's also where high resolution sampling can come in. And that's why we use multiple types of proxies because each of them has slightly different controls. So delta 18O is going to have a very different response from magnesium, calcium in different cases, but the fact that they are overlapping suggests that it is a drought-driven type change to us.
Great. So our next question says, nice talk. Do you think that the drought length was key to the impact on civilizations? And do you have any ideas on the climate dynamics behind such long drought intervals?
Yeah, I love this question. So part one of does the length matter of the drought? And my answer based on the conversations I've had with archaeologists is that yes, the length definitely mattered because the water storage systems that were present at Teotihuacan would have maintained water for about months to a year, that scale of things. And so they were really adapted to this aquifer that could constantly be recharging, or to seasonal rainfall that would come. And even if there was no rainfall in the winter, because this is a summer rainfall area, they could wait that out until the summer rains came. And so if there was a dry year or 2 years, I think that that was more recoverable. But if there just was no water left, even in the aquifer, or very little, that would have been a major issue. And so I think especially with the droughts that we're seeing here that are on the longer side, I think that probably played a significant role. But that's something that we're talking with the archaeologists more about because that's not our specialty. And then the second question was about, oh no, I already, it was like the big question. Well, can you repeat it?
The second question, the second part of it was, do you have any ideas on the climate dynamics behind these long drought intervals?
Yes, of course. So yes, that's something that we're working on with Tripti Bhattacharya, especially because she does a lot more of the climate dynamics and modeling parts of it, but we're looking at interaction between the Atlantic Ocean and this area. And so for the most part, we're looking at those like sea surface temperature ocean interactions with precipitation. So we're looking at mostly the AMO or AMV and trying to identify whether there's a El Nino signal in there, but so far we're not seeing one. But because of the changes in resolution that we have in sampling, we're hesitant to say so far, like there's no El Nino signal in this slide. So far, most of what we're seeing in terms of kind of the spectral analysis that we're doing is a multi-decadal signal, potentially that AMO or AMV.
Excellent. So we're getting a lot of questions coming in. So I just want to say that I think we've got like 4 or 5 left, and we want to hit everyone who's asked a question thus far. But at this point, if you have more questions you'd like to ask Gabi, please feel free to pop into a breakout room to discuss them after, or stick around for tea time. But just to get to the ones that have come in, the next one asks, did you look at how Speleothem records compare to late Holocene lake records in Mexico?
Yeah, that's in progress for sure. Juanacatlan is one of the records that we included in our EOF, and that is a lake record. So we are trying to add more of those. The issue that pops up sometimes, as I'm sure all of us know, are age model errors. And so we are trying to find sites where there are age model uncertainties that are comparable to the ones that we're working with our speleothems. And so if you have any suggestions for sites that you think I should really look at, I'm happy to hear about those, because I always want to hear about more data and more sites that maybe we've missed, and looking at like the NOAA database and all that. So happy to take suggestions on that, but we are working on that.
Great. So our next question asks, do you have any thoughts about why your record shows a single elongated period of drought compared with Medina Elizad's increased frequency of shorter droughts in the Yucatan?
Yeah, that's like the big question. I think we are still working on that. To my understanding is that we're still working that out. Part of it could be a difference in whether this is Pacific derived moisture or Atlantic derived. This is a site that has almost exclusively Atlantic moisture coming in at this point. I didn't include the trajectory figures I have here, but we did a trajectory analysis and we're seeing that there is a strong seasonal signal here, and that a lot of it is from the Atlantic. And so I think that's a big part of it. And because we don't yet have the Delta 18O and Delta 13C over this exact same area, I'm hesitant to call that super confidently almost 100-year-long drought, a 50-year-long drought. And it's possible that those with a higher resolution analysis could pop up to just be frequent short droughts. And so I don't want to say really concretely that that's not the case, but so far what we're seeing is this long one. And then we're not seeing a lot of frequent kind of increases, even where we do have higher resolution data. So we do have high resolution data across from basically here to here, and we don't see those frequent spikes up. So, so far we're not seeing them, but that's definitely a question.
Just as a follow-up to this, there's also the question of, is it possible that the decadal droughts, or that you see decadal droughts in the past and not in the modern because of the stalagmite sample resolution? I think you answered some of that, but if you have some more thoughts.
Yeah, the resolution, I think we'll be able to get to closer to annual resolution for the faster growth periods. The part where it grew more slowly, it's going to be a lot more difficult, because then we're talking about like sub 0.2 millimeters worth of sampling. So just in terms of the amount of powder we need and the drilling capabilities, that might be one of our limiting factors. But yes, that is something we're thinking about, and that's part of why we want to try to fill in those gaps in data with just a few more points.
Excellent. So we have two more questions. The first one says,
oh my goodness.
I know, from Tripty's 2017 QSR paper, what drives the hydroclimate dipole in Mexico? And I think you've addressed that a little bit, but.
Yeah, I'll just go back to her figure because she showed it so nicely. But the main sort of response difference, or the thing we mostly talk about in terms of the dipole, is what happens when Atlantic sea surface temperature is warm or cool. And so personally, I'm not super clear on, why is it exactly here, and why is this sort of like the split point between the two. But we're doing trajectory analysis, which just shows where the modern rain parcels are coming from and where they're ending up and where they dump out their water. And so for the most part, we're seeing that these southern sites here, especially Huxtlahuaca down here, if I'm remembering correctly, has a lot more Pacific derived moisture. And over here in Belize, there's not as much Pacific derived, but there's less of a strong summer signal. It's more distributed throughout the year when that precipitation is happening. Whereas up here in the north, we really have a super clear Atlantic and summer specific moisture source and time period. So I think that might have something to do with it. And just sort of, this is approximately where we're seeing the split in terms of that trajectory, but that's something that we're continuing to work on.
Great. And then just one final fun question. Someone asks, what is your favorite part about fieldwork in Mexico?
Ooh, that's a great question. So my mom's family is actually from Mexico, and so I love being able to go there and speak Spanish and eat food that's really familiar to me. And I feel like it's a place and an experience where the fact that I speak Spanish becomes super valuable. even though during my day-to-day science life, I don't really use my Spanish. So it's a great time to practice that. And I think overall, the food is way up there. I drink a lot of Coke and eat a lot of quesadillas. So I'm a very, very happy camper when I'm doing field work there. I miss it a lot.
Well, on that very wonderful note, what I'd love to do is thank Gabi for her absolutely excellent talk. I'm going to pop up our last couple of slides for the roundup of housekeeping. And we'd like to invite you to stick around. So thank you, Gabi, for your very wonderful talk. And thank you all for joining us. We'd like to remind you to, if you're here, please fill out the SurveyMonkey link for today's talk, just so we know who's coming to these things. And we'd like to ask you to join us for next week when Jorge Kardich is going to be presenting on the paleoecology of benthic foraminifera and anoxic sediments, the reconstruction of the OMZ off Peru in the last millennium. So we're going to have some more climate of the common era going next week as well. And then we'd also like to encourage you to stick around for the next few minutes of small group discussions. So you have the opportunity to meet some new friends, bump into some old friends, discuss this talk with paleo fans from different backgrounds. That's a really big thing that we like to have here at Paleo Perks. And so we'd also like to encourage you to, if you stick around for a breakout room or stick around till the end of the hour for tea time, when you get to your breakout room, please introduce yourself. And if you need a thing to discuss, our question of the week is, what type of weather or climate process do you wish there was a proxy for?